Hello, my name is Nikolaos Mathodonas, and I'm a PhD student at ECMWF and TEO Academy Freiburg. This talk is about the predictability of large-scale atmospheric flow patterns connected to extreme precipitation in the Mediterranean, and is supervised by Linus Magnusson and Florian Papeberger at ECMWF and Jörg Machulat at Freiburg. We know that extreme precipitation has devastating consequences in our societies and economies, and one way to mitigate their impacts is to know when and where such events are expected to occur. So the motivation behind this work is to analyze and quantify if and how some large-scale patterns can be used as predictors of localized extreme precipitation events, and how useful can this connection be for the different lead times of forecasting. And let me navigate you through the presentation that we will start with the precursors. So some work that was previously done that identified 9 patterns over the Mediterranean and their connection to localized extremes. And of course move to the datasets and the variables that are used for this study, and describe the methodology afterwards. The methodology for assessing the skill of the ECMWF extended range forecast for predicting the 9 Mediterranean patterns, and for indirectly providing information about extreme precipitation events. This will be shown in some results, and we will end up with the main conclusions over this work. And here we see the 9 patterns over the Mediterranean, they're composites. These patterns were derived based on empirical orthogonal function analysis and subsequent K-means clustering of 2 atmospheric variables, namely the daily anomalies of sea level pressure and geopotential height at 500 hectopascals. And in this plot here, we show the composites with blue color refers to the negative anomalies of sea level pressure, and red the positive anomalies of sea level pressure. And essentially the first 6 patterns refer to some negative anomalies that are propagating over the very west, so the Atlantic low, up to the very east, the Biscay low, the Black Sea low. And then we have 1 pattern of high pressure over the whole domain, Mediterranean high, and 2 patterns that can be considered as non-anomalous over the Mediterranean in general. So these are the minor low and minor high patterns. And let's see now how these patterns are connected to extreme precipitation. And this is shown on the upper right figure, which shows which of these patterns is preferentially connected with extremes at the different subdomains. And we see that each pattern is connected actually to different sublocations. And for instance, if we check the locations over northwest Italy or West Balkans, we see that the preferential pattern is the Biscay low. So under this configuration, this quite physically makes sense, because when we have a low pressure of the Bay of Biscay, under such configurations, the airflow and subsequently the moisture goes towards Italian peninsula and the Balkans. And let's now quantify these connections, which refer to results for the 95th percentile extremes. So the nominal probability of the extremes is 5%. And we see that the cluster of maximum condition probability has around 3 times higher probability from the nominal for most of the domain. But especially for areas of high orography or the coasts, for example, such locations here centered, we see that the probability is actually 4 and 5 times higher than the nominal. So very strong connections that give us the motivation now to start the predictability of these patterns, and of course how useful they are for indirectly predicting extreme precipitation localized. And for this work now we use 2 datasets, the ERA5 reanalysis and the ECMWF reforecast, the extended range reforecast of cycle 46R1, which has 10 perturbed members and 1 control member. And essentially we have 2,200 dates for its lead time from 0 to 45 days ahead. And as for the variables, we use the sea level pressure and the geopotential height, and of course the precipitation information. So going to the methodology now, we have 2 streams. The lower stream refers to the large-scale variables, and the results from the reforecasts and the ERA5s or ground truth. And the first thing that can be done, of course, is to get some aggregate errors, like the anomaly correlation and the root mean square error of our reforecast model for the different lead times in comparison to the ERA5. Our main information, what we really want, is to allocate now each of the reforecast fields to one of the 9 patterns, and this is done based on the Euclidean distance. And we allocate the reforecast to the pattern that has the minimum Euclidean distance from the composites. And once we have, of course, these allocations, we can get some statistics of the reforecast and the patterns, like the frequency of the patterns, and of course the Breyer score. And we can compare this score with some reference, which in our case is the 91 days moving window climatology and the Markov chain, so transition probabilities persistence. As for the second stream now, we have the data of course, for the large-scale variables and the precipitation from the era 5 now. And the first thing we have, as presented in the previous slides, is the conditional probabilities of extreme precipitation given each of the 9 patterns. But the question is really how useful is this connection, this subsetting in general, how much discriminatory skill it has for extreme precipitations in a long-term basis. And this can be again assessed based on various score and various skill score. And in the case of extreme precipitation, the benchmark is a 31 days moving window climatology occurrence of extreme precipitations on the different grid cells. And now that we have the connection of patterns to EPs and the forecasted patterns, we can once more time use the prior skill score of now inferring extreme precipitation given the forecasted now Mediterranean patterns. And let's move to the results. And here in the first result we have the anomaly correlation coefficient for the different lead times from 0 to 45 days. Of course, we care for results that are over 0.5. And here we have different colors. So the green color refers to the ensemble mean, so one artificially created member, the average of all 10 plus 1 members of the reforecasts. And then we have the control member, the blue color, and the ensemble members, the perturbed members, which is the orange color. And these results refer to the median for the 2,200 dates for each of the lead times. And given our threshold of 0.5, we can see that the model is behaving well up to around 10 days lead time, with the ensemble mean having a better performance, as it seems, but of course it's a bit misleading, as we will see later on. And let's observe now what's happening with the frequency of the patterns for the different lead times. And here we have the lead time of essentially 0 days, so below 24 hours ahead. The 3 first bars refer again to as before, to control member, perturbed members, and the ensemble mean. And the last bar is the era 5 frequencies, so our ground truth for the subset of dates that refer to the 0 days lead time. And of course what we want is that the first 3 bars are very, very close to the last bar, so there is no bias, no error. And this is the case for 0 days lead time. We see that the results are very, very similar. And let's see how this works for the different lead times in this small animation. And we see that the results are actually quite good, but after essentially 8-9 days ahead, the ensemble means start having a very big bias of overestimation of the minor low pattern. We see that the green bar is very high, and this of course results in essentially no information about some patterns like Mediterranean high and Balkan low. And why this is happening? Because of course of the chaotic nature of the weather, the perturbed members start behaving very, very differently after some days. And in such cases, we have, for example, some members showing some negative anomaly over the west Mediterranean, let's say Atlantic low, Biscay low, some others showing a negative anomaly over the East Mediterranean, for instance, Black Sea low. And obviously when you average all this information, you get a pattern that is non-anomalous in general throughout the domain. And this is of course referred to as minor low in our 9 patterns, and also minor high, where there's also a bit of bias here. The positive thing is that the actual members of the model, the control member and 10 ensemble perturbed members, they don't seem to have some strong biases. So the bars we see, they're very comparable height with the last bar, which is very good. And let's move now to the results for allocating the 9 patterns. And here we present the results with a fair Brier score, and in fact the results of Brier skill score, so compared to our benchmark units for winter half. And we select winter half because there is a bit more variation of the skill for the different patterns, and also during winter half we have most of the extreme precipitation over the Mediterranean. And what we see is that given these metrics, our model, the ACMWF model, performs quite well and beat climatology in already up to week 3, so over 15 days. It's around 18 days, we can say, the limit for most of the patterns. We have now one pattern, the minor low, that is behaving quite poorly compared to the others with a 10 days limit. And then we have also the Mediterranean high, which has a higher performance, especially for extended range forecasts, with over 20 days, we can say. Almost we can go to week 4 even of skill for such pattern. And now, before we present now the results of the lower stream, you recall, from the methodology to assess the skill of the ACMWF for really predicting the patterns. But if we go now to the second stream in the methodology, and we want to see the discriminatory skill of the patterns for inferring extreme precipitation. And here we have the results again for the 95th percentile extremes, and the Brier skill score point conditioning for extremes based on which pattern we have at each of the days. So this refers essentially to the best results we can get if we had a perfect forecast, if we were pretty sure that every day we have the correct allocation of the patterns. And here we have masked the results, and we show only places where the Breyer skill score is positive, so we beat the climatology. And we see that this happens pretty much everywhere besides the East Mediterranean. So in East Mediterranean we cannot beat the climatology with these 9 patterns, because in these locations the extreme precipitation is really seasonal. But what we see for the other places that we beat it, of course, there is not a very high increase in the score. We have like 2% on average, a gain of skill. But what we care of for locations of hydrography and coastal areas, which we have also a lot of population, this subsetting can give a over 5, 6, and even 10% skill. But what if now we make a bit of temporal subsetting as well? As I said, the extreme precipitation is very seasonal. So what if we provide the condition probability of extreme precipitation given the pattern, but also given the half-year statistics? So is the pattern observed in winter half or summer half? And when we do this classification now, so essentially we have now 9 multiplied to 18 different condition probabilities, we see that we can beat the benchmark score pretty much everywhere. And we have also a bit of increase in the skill. The pattern we see is again the same with coastal areas and hydrography places having a higher score, over 7%. So this, as I said before, is the best skill we can get. We have a perfect forecast. But now, if we use the forecasted patterns and the condition probabilities of the forecasted patterns of each of the members, of the 11 members of the model, and the condition probabilities based on the ERA5 data, can we beat the climatology, and up to how many days ahead for the different locations? And here we have these results. Here we show with the different colors the forecasting horizon. So up to how many days ahead we can outperform the benchmark score for extreme precipitation events when we use the forecasted patterns of the model and their conditional probabilities for inferring EP's statistics. And we can see that this actually happens for most of our locations up to the end of week 1 and start of week 2. But once more time, for locations of hydrography and coastal areas, this goes a bit further beyond, so we can go up to 10, 11 days ahead for places like West Turkey, West Balkans, West Italy, and of course Iberian Peninsula and Morocco. So we see that just by conditioning based on these 9 Mediterranean patterns, considering the half-year statistics now, summer half and winter half, we can beat the climatology and the benchmark score for observing extreme precipitation events up to 2 weeks ahead for many of the locations. And if we sum up and conclude now, we see that first of all, the ECMWF model seems to have no important bias for the actual members, the control member and the 10 perturbed members. And there is only very high bias after week 1 for the artificially created stable mean, which of course should be avoided. The model, moreover, seems to outperform the benchmark scores in terms of forecasting the 9 Mediterranean patterns up to 3 weeks lead time, even 4 weeks lead time for one of the patterns in the Mediterranean high. And finally, we can use these forecasted patterns for beating the score of the climatological scores of now extreme precipitation events, even up to 1 or even 2 weeks ahead, depending on the location. Quite promising results for providing useful information for even subseasonal scales, a bit the start of subseasonal scales. And this results give us motivation to study some other questions, as for example, to compare these results with the forecasting EPs based on other predictors and their forecasted values from the ECMWF model. For instance, the water vapor flux, which is very strongly connected to precipitation, but of course the actual precipitation forecasting fields of the ECMWF model. And finally, assess if and how some teleconnections affect the formation of these 9 patterns, and if also we have some source of predictability that can enhance and give more confidence to the results of the ECMWF model, mainly for subseasonal scales. If you have some comments or some questions, you can get in touch with me, of course, via email or Twitter, and do not forget to join the VPICO session on 30th of April, 11:35 CT. Thank you for your time, and see you at the GU.